Previously, after reviewing the relatively slower algorithms, we looked into merge sort, which has a n log n time complexity. We expanded on how merge sort requires us to have an extra auxiliary memory space of equal size of the array. In this video, we will look into an algorithm that doesn't have this memory overhead, and in most cases, it is even quicker than the merge sort. The Quicksort algorithm. Welcome to CodeStation. A pivot is a pin, a shaft, or a point about which something rests, turns, oscillates, or rotates. A pair of scissors, for example, turns about a pivot. Similarly, many other machines in our practical life depends upon a pivot. Most significantly, a seesaw that rests completely on a pivot. The Quicksort algorithm relies on an idea of choosing a pivot element among the elements in an array and sorting this element. Like merge sort, Quicksort is also a divide and conquer algorithm. We divide the problem domain into smaller problems. This division happens at the sorted pivot element. Basically, we select the pivot element first. Then, we sort the pivot element using an algorithm called partitioning. After that, we'll perform quicksort at the left side of the pivot and do the quicksort at the right side of the pivot in the array. Let's go through these steps one by one. Selection of pivot is integral to the algorithm because the speed of the algorithm depends upon this. For an ideal case, the pivot should be the median element. But how can we recognize the median element without sorting the array, right? So a simplistic approach is just to choose the last element in the array as the pivot. In this video, we will just use this approach. However, other approaches of selecting either the first element or the element at the middle is as good as this approach. What is a sorted pivot element? Well, it means that the pivot element is placed in the array such that its spot remains the same when the array is sorted. This would be the case if all the elements before the pivot are smaller than the pivot and all the elements after the pivot are larger. So for example, in this array, the last element 12 is sorted because all the elements before it are smaller than 12. Similarly, in this array, the first element 0 is sorted. All the elements after this element are larger than 0. In this array, a middle element 4 is sorted because all the elements to the left are smaller than 4 and all the elements to the right are larger than 4. We mentioned earlier that we use partition algorithm to sort the pivot element. This is the partition function to partition a subarray of an array starting at a low index till a high index. We will set the last element of this subarray, that is array element at high, to be the pivot. Index 1 is set to be at the first element of the subarray. Index 2 is set to be at high minus 1, which is the second last element of the subarray. Now the actual loops begin. Here the outer while loop continues until index 1 is less than index 2. In the inner loop, we first move index 1 forward till the element at index 1 is greater than our pivot. Here 12, which is the second element in the subarray, is greater than the pivot 6. So index 1 is set to this point. Then we move index 2 backwards until element at index 2 is smaller than our pivot. Here, we don't need to move index 2 backwards as 5 is already smaller than 6. Here index 1 is smaller than index 2. Therefore, elements at index 1 and index 2 swap. Notice what happens now. Consequently, the element at index 1 is now smaller than the pivot and the element at index 2 is greater than the pivot. Since index 1 is still smaller than index 2, we continue the outer loop. Index 1 moves forward again until the element at index 1 is greater than the pivot. Similarly, index 2 moves backwards until element at index 2 is smaller than the pivot. Here, index 1 is now greater than index 2. Therefore, no swapping is done between these indices. The outer while loop ends as well. This loop, iterations of index 1 and index 2, and the swapping operations essentially partition the subarray into two parts. The left part until index 1, where the elements are smaller than the pivot. Then, the right part at and after index 1, where the elements are larger than the pivot. The next operation is to swap the pivot element with the element at index 1. This moves our pivot to index 1 position and make sure that all the elements that are left of the pivot are smaller than the pivot and the elements at the right of the pivot are larger than the pivot. This sorts the pivot element. The partition function will then return the index at which the pivot is present, that is index 1. The quicksort algorithm essentially calls the recursive doQuicksort function that sorts a subarray starting at a low index and ending at a high index. As we can clearly see, this function is recursive. Well, we sort the pivot element and obtain its position using the partition function, and then we call itself again for the left subarray until the pivot position, and the right subarray after the pivot position. Thus, we divide the problem and conquer our sorting. Let's look at an example. This is an array with 11 elements. We would call the doQuicksort on the whole array first. Partitioning would set the 10th element as the pivot, 0th element as index 1, and 9th element as index 2. Index 1 element 5 is already greater than pivot of 0. Thus, it does not move forward. Index 2 moves backwards and doesn't find any element smaller than 0. Thus, the swap happens between index 1, that is the 0th element, and pivot. The element 0, which was the smallest element in this array, gets sorted and placed in the 0th position. The partition function returns 0 as the pivot index. There is no subarray before 0, therefore doQuicksort call in the left partition doesn't have an effect. doQuicksort on the right partition similarly sets the pivot as the 10th element. Index 1 is set as the first element, and index 2 is set at the 9th element. What do? We move index 1 forward until we find an element greater than pivot. We find this in second element itself. Then we move index 2 backwards until we find elements smaller than 5. Index 2 moves all the way to the first element. Index 1 is greater than index 2. Therefore, the outer while loop ends. We swap index 1 with pivot. Element 5 is sorted. After that, we run the doQuicksort on left subarray. The left subarray has just one element, and thus it is already sorted. doQuicksort is performed on right subarray. Pivot is 18. Index 1 moves to the 8th element 20. Index 2 doesn't move here, as index 1 is smaller than index 2. We swap these elements. The outer while loop continues, moves the index 1 forward to the 9th element, moves index 2 backward to the 8th element. Index 1 is now greater than index 2. The outer while loop ends, and the pivot swaps with the element at index 1. Similarly, we move on to the next level, continue partitioning in the left subarray, and perform quicksort recursively as demonstrated. After all these partition operations on the recursively called subarrays, we finally get an array that is completely sorted. In the worst case, the complexity of this algorithm is order of n squared. This would be the case when we do n iterations to figure out that the pivot belonged to either the rightmost or the leftmost position. Thus, after the partition, the doQuicksort function would be called in an array of size n-1. Similarly, for this array, we do n-1 iterations to sort the pivot element. We would then pass an array of size n-2 in the doQuicksort function. If this pattern was followed throughout, we would get the worst case performance. The complexity calculation is the summation of similar series that we saw in our bubble sort video. That is summation of 1 plus 2 plus 3 until n. Remember the dots and how they made a right angle triangle? This summation is equal to n times n-1 divided by 2. Asymptotically, this would be order of n squared. When would we get this worst case complexity? Perhaps when we have a completely unsorted array, right? If we have an array that is sorted in a descending order, and if we need to sort it in an ascending order, how would we do this using quicksort? Well, with our approach of setting the pivot as the last element, we would compare the pivot with all the previous elements to realize that it should be at the beginning. Then the swap happens. Pivot is now the largest element. We do n-1 comparisons to figure out that this is the largest element and no swap is necessary. Then the pivot would be 3. The smallest element and subarray of n-2 size that we're looking at. We would still need n-2 comparisons to figure out that this is actually the smallest element. Then n-3 comparisons, and so on. Thus, we demonstrated the worst case performance of order of n square here. But in the initial completely unsorted array, what would have happened if the pivot was the middle element? Let's observe. The pivot would have been 4. We would swap index 1 and index 2 as element at index 1 was greater than 4, the pivot, and element at index 2 was smaller than 4. We would move index 1 to the next position to the right. We would move index 2 to the next position to the left. We would swap again. This would be the end of our first partition. The pivot element would stay unchanged. We still did n iterations in this level. Then we would divide the problem down into left subarray and right subarray. We would approximately do 2 n-by-2 comparisons to figure out that they are already sorted. And that's all. We only had to do order of n log n iterations. So really, for the same problem, we got a better performance when we changed the pivot in our operation. Actually, order of n log n is the best case complexity for the quicksort algorithm. This is observed when we could equally divide the array into halves at each level. Unlike the merge sort, we don't need to have an overhead of merging the arrays back to the previous array. Therefore, the total number of iterations is in the order of n log n. In fact, on average, a quicksort algorithm's performance is in the order of n log n. Like we've seen earlier, the complexity of quicksort algorithm depends upon the pivot that we choose. For a quicker performance, one way to choose the pivot is to take the first, last, and the middle element, sort them using insertion sort algorithm because it is efficient for a small dataset, and find the median among these three elements. This element could then be chosen as the pivot. Similarly, there are randomized quicksort techniques too, where we select a random element at the subarray as the pivot. These techniques help improve the quicksort performance. Compared to merge sort, quicksort requires lesser auxiliary space. Quicksort is an in-place sorting algorithm, while merge sort requires an order of n space for the merge operation. We have discussed that the worst case performance of quicksort is order of n square. Practically, however, this performance is very rare and can easily be avoided by good pivot selection technique. Quicksort algorithm also exhibits a better cache locality in the processor compared to the merge sort algorithm. Therefore, in most cases, quicksort is generally faster than the merge sort algorithm. However, quicksort is not a stable sorting algorithm. If a data structure is large and if it has many members, there is a chance that two objects are equivalent. In this case, quicksort might produce different sorting results based on where the pivot is. For example, let's say we have an array with animal 1 and animal 2 as demonstrated. The sorting criteria accounts for height, weight, and age, but not the color. Thus, animal 1 and animal 2 are equivalent based on the defined comparator. If the pivot is chosen to be the first element, we sort it such that animal 1 comes before animal 2. Similarly, if we choose the pivot to be the second element, we would sort animal 2 before animal 1. Of course, this instability can be avoided by choosing better comparator. If a better comparator is not possible, and if you require stable sort, using merge sort algorithm would be an option. In general, the merge and quicksort are widely used in the real world for sorting purposes. For larger dataset, we would see improvements in order of 100% for the number of comparisons. Moreover, by design, these divide and conquer algorithms could be run in parallel. One half of the problem could be run in one processor and the other half could be run in the other. Therefore, there is a big motivation to use these algorithms for larger datasets. In the recursive calls, when the array size eventually gets smaller, we could easily switch to insertion sort for better optimization, just like we mentioned in the insertion sort video. In the upcoming video, we'll learn about an algorithm that is conceptually a little different than the sorting algorithms that we have looked at. I hope you liked this video. Please let me know if you have any questions or concerns. Also, please like and subscribe to my channel for more videos like this. Thank you for watching.